All right. So in today's lecture, let's go forward with differential pairs and do an analysis and see what their properties are. So as usual, the first thing that we do when we take an amplifier, we take is bias point analysis, bias or quiescent point analysis. And for that, if I take my differential pair, I remove my input voltages. Their voltages inputs are removed, and then what we need to do is look at the currents flowing in the transistor. Okay, so what we see here is that we can calculate the current flowing in this particular branch. We know the voltage here is minus 0.7 and minus 0.7 minus VE by RE, so that gives us this current. And in differential pairs, we construct them by taking transistors Q1 and Q2, which are as close as possible in the characteristics to each other. So we say that they are matched. Q1 and Q2 are matched transistors, and therefore, since the base emitter voltage is the same, the transistors are identical, so the current through Q1 and Q2 are also identical, which we get as half of IEE here. So half the current flows here and half the current flows here. And once you know the current here, you know VCC, you know the DC value of the voltage here, the DC value of the voltage. All right, so that's straightforward calculation of the bias point here. Now, small signal analysis. Very often, another place that is used, another name that is used for small signal analysis is AC analysis. But here we have to be a little bit cautious. In the previous amplifiers, the signals that we were applying were AC. But this amplifier, note that when we say small signal can be a small DC, AC, anything. All right, it's just a small signal. Even though we call it AC analysis, the signal is not really AC. I may have used the symbol AC here. This voltage can be a small DC voltage also. All right. The difference is, if you're wondering, in this case also we have done a DC analysis. This is not DC. The proper name for this is bias point. So we have taken an amplifier which is biased at a certain point. So that's a bias point. It just happens that, yes, the biasing is done through a DC voltages and currents, right? So it's a bias point analysis here. And the next one is a small signal analysis. The small signal could be a DC, AC, square wave, whatever it is, but it has to be small in nature, which we have seen earlier, for small so that we can apply a linear model of the transistor. Hybrid pi model is a linear model, so that's why we call it small signal here. So note that because there are no capacitors in the circuit, therefore I can amplify a small DC as well. In the previous circuits, because the coupling was done through capacitors, the DC amplification was not possible. So that's why we also call it a DC amplifier here. Anyway, so this is the circuit that we have to analyze. In general, we can have V in 1 and V in 2. We can have both the signals. And so I was telling in the last lecture that what we can do is we can analyze the behavior of this particular amplifier in terms of its response to differential signal. Differential signal is defined as the difference of the two, V in 1 minus V in 2. And we can look at its response in terms of the common mode signal here, VI1 plus VI in 2 by 2. So the input signals that you've applied can be thought of in terms of a differential mode signal and a common mode signal here. You can easily see that I can write V in 1. Once I define VID and VIC in this manner here, I can write V in 1 as 0.5 VID plus VIC and V in 2 as minus 0.5 VID plus VIC. I can rewrite them in this particular form here. All right, so the properties of differential pair are best understood in terms of differential input signal and common mode input signal here. All right, so with those definitions, what I can do is I can take V in 1 here and V in 2 here, and instead of them, I can put here 0.5 VID plus VIC here. Note that V in 1 is this one, and V in 2 is minus 0.5 VID plus VIC, so you see it here. All right. So instead of V in 1 and V in 2, the two input voltages I put in terms of VID and VIC. All right. So now what we'll do is, as I said, our interest is in understanding how does this differential pair respond to differential signal and how does it respond to common mode signal here. So what we are going to do, note that we are doing small signal, and in small signal my transistor is being described by a linear model. And so the whole circuit is linear. and linear means I can use superposition. All right. So this analysis, now what we are interested in knowing what is V01 and V02. So this analysis, we can break it up into two analyses. I can find out what are V01 and V02 first due to differential signal, 0.5 VID here and minus 0.5 VID here. Then I can find out what are V01 and V02 to common mode signal here. And then the two of them, whatever V01 I get here, whatever V01 I get here, I can add them up to get the net V01. Because it's a linear circuit, I can use superposition. Okay. So analysis, general analysis is being broken down into two analyses, differential mode and a common mode, where the signal is purely differential mode here and the signal is purely common. The signal that is applied here and here are identical. The signal that is applied here and here are exactly same in magnitude but opposite in sign. So it's a pure differential signal. It's a pure common mode signal here. So note that any signal at any point in my circuit, you know that in general signal at any point in your circuit is whether it's voltage or current is made up of a bias point, a DC, plus a small signal. That we've already seen. In an amplifier, we have two things, a bias point and we have a small signal part here. Small signal could be AC, DC, whatever it is. Now what we are saying is the small signal part can be broken down into two parts here. A differential part, small signal, and a common mode, small signal here. So overall signal here, so differential part and common mode. So we are further breaking it down into two parts. So differential part will be related to, let's say if this is the output, differential part will be related to the input differential voltage. And the common mode part would be related to input common mode voltage. Right? So this is how the total signal is. Bias point, of course, is through DC voltages and currents. Small signal part arises from differential part here and a common mode part here. Okay? Alright, so for example, if I want to know the total value, note the total value of the output voltage here, V01. The total value of V01 would be the bias point V01Q plus a V01 differential. V01D is what? Coming from differential signal, differential input signal. And V01C coming from common mode signal. So except that, note that this used to be one single small signal voltage. We have broken it down into two parts, differential and common mode. So all analysis in differential pairs is done now. Two times we have to do a differential mode and a common mode. So differential mode V01D will be related to VID, to differential signal through what? A differential mode gain. And common mode output voltage will be related to common mode input through a common mode gain. Alright, so note that total analysis involves bias point, again small signal is differential mode and common mode. And everything is made up of these three parts here. Alright, so let's not forget this part here. So let's do a differential mode analysis then. So we take our differential pair and we apply plus 0.5 VID, minus 0.5 VID here. And we want to analyze what is V01 and what is V02, maybe what is the input resistance. And output resistance is straightforward. When I look from here is only RC here. So that's straightforward here. So let's do this analysis here. Now if you note, if I look at this particular circuit, note that Q1 and Q2 are identical. RCs are the same on both sides. RE is common. I apply a plus voltage here and I apply a minus voltage here. What is the voltage at this point? Can you all see what the voltage at this point would be? We are talking about small signal. What would be the small signal voltage here? Without doing any analysis, look at the circuit and tell what is the value at this particular point. Plus here and minus here. So what does this, if I increase this, it tries to make this higher, positive. And what does this try to do? Tries to make it lower. What is this point here? This point will try to make this positive. This point will try to make it equally negative. The value of this voltage is 0. From symmetry, we can tell that this point has to be 0. If I put plus 0.1 volt here, I put minus 0.1 volt here, there cannot be any other value except 0. Alright, so that's what we'll do. We'll put here 0 volt. But remember, I'm cautioning you, what is this 0? the 0 is small signal ground. It's not a DC. Note in DC, this value was minus 0.7. So very often we confuse DC with small signal and all that. So this is a small signal ground for differential signal. Is just that we are taking it as a ground for the purpose of analysis. Okay. So this becomes 0, small signal ground. And then note, then the two circuits, they separate out. Okay. So this point becomes ground and this point becomes ground here. So it becomes like this here. That's what the circuit becomes. Left half circuit becomes here. Right half circuit becomes exactly the same here. This point is ground. It becomes of this kind. Okay, so the two halves separate out. And this now looks like a normal common emitter amplifier. Common emitter amplifier. And you know the gain of this amplifier, V01D, would be minus, because this is 0.5 VID. So that's why 0.5 VID. And the gain is minus GMRC. So that's what we write. V01D is minus 0.5 GMRC VID here. If I look at this side here, the right hand side was also ground here. So the output voltage would be again the same gain here, minus, but minus and minus they cancel, and so you get plus. So you get V02D 0.5 GMRC VID. So what you find is that the voltage here is this value here, and the voltage here is exactly same but opposite in sign. And the gain now, gain is V01D, the output voltage here, divided by VID. We define the gain of the differential pair not as V01 divided by 0.5 VID. We define the gain of the differential modes, differential amplifier as what is the output voltage here divided by the net differential input voltage here, which is VID. So with a V01D by VID is minus 0.5 GMRs. So that becomes our differential mode gain. All right. The gain from this side is also the same. If I want to write V02 divided by VID, I'll get 0.5 GMRC, except that I'll get positive. So the voltage here and the voltage here are the same in magnitude, but opposite in phase. Okay. All right. So as I said, differential amplifiers can be thought of as amplifiers. All differential amplifiers will have two inputs. I can think of output as this as an output or this as an output. Sometimes what people do is they take the difference of the two as an output. V01 minus V02 as an output. They define the output voltage as that between these 2 points here. If I do that, V0D, that's called a differential output voltage. Okay, when I note that when I say this is the output, what do I mean? Between this node and ground. That's my output voltage. If I say this is my output, I define it as between this node and ground. A differential output voltage is between this and this here. So the difference between V02 minus V01, and because the two are identical and opposite in sign, so it becomes GMRC. So that's the differential output voltage here. This is differential output voltage here. Why? Because it's the difference of the two voltages. The previous one was a standalone output voltage here. Okay. All right. Let's look at the differential input resistance then. So the gain was straightforward. So differential input resistance. So what we are asking is, when I look from here, from this point, what do I see? How much resistance do I see here? Okay. So note that when I look from here, how much resistance do I see? It would be equal to 0.5 VID divided by the current here. All right. So the differential input resistance is then defined as the net differential input voltage here divided by the current that flows over this particular point here. And so let's do that. Again, this point is small signal ground. Small signal ground. And it's easy to see that the resistance that I see from here, the current that flows here is 0.5 VID by R pi. And so we can take the ratio VID by I, total differential input voltage divided by the current, and the resistance turns out to be 2 R pi. All right, so that's the net resistance that we define for differential mode operation here. Output resistance we have seen is already same. Output resistance at this particular point is ours. So that's not an issue here. Okay, so let me just summarize. When I'm taking output at any particular point, V01 or V02, what we are getting is a differential mode gain, 0.5 GMRC. RID is 2 R pi. R0 is RC. These are the characteristics of the differential pair that I get under differential mode. If you look at ADM RID by R0 is also equal to beta. Because note that even though the differential pair is two transistors, but when I look at it in the differential mode, it's nothing but like a common emitter amplifier. Okay, go back and see that this point becomes ground and each half is nothing but a common emitter amplifier. Okay, so its characteristics are also, note the expressions for the gain 0.5 GMRC, RC here, R pi here, except that because there are two halves and the signals are divided, you get a factor of 2 and you get a factor of half here. All right, common mode analysis. Let's look at that. So in the common mode, note that the signal is the same at both sides. Signal is the same at both sides. And again, in all these amplifiers, what we try to do is use symmetry. Use symmetry to simplify. Okay, because the transistors are matched, the signals on both sides are the same. And therefore, why do a more complicated analysis when we can simplify it? So let's look at the steps here. So the currents are the same. IC here. When I apply a small signal here and a small signal here, there would be a small signal collector current. There would be a small signal emitter current. The two emitter currents will add up and will go to ground. All right. Note the 2 points here. This one here, can I write it like this? The other resistor that you see here, REE, I'm splitting into two resistors. 2RE in parallel with 2RE. Fine. Because of symmetry, IE should flow here and IE should flow here. Earlier, these two were one single resistor and the net current was 2IE. Now I split it into two resistors, and from symmetry I know a current IE should flow here and a current IE should flow here. No problem so far. I'm using symmetry here. If this is true, note that what is the current here? IE. And what is the current here? IE. What is the current in this? 0. So if the current is 0 in this branch, I can open it. I can remove this. If the current is 0, whether I keep it or remove it, it doesn't make a difference. Right? So now note that by symmetry what has happened is the two halves have become separate. This half now is separate from this half. The two halves are separate. So effectively, and note that I have to calculate the voltage here. So the voltage here and the voltage here are identical. And I don't have to do a two transistor circuit analysis. I only have to do a single transistor circuit analysis. So we break the circuit into two halves and we take this particular part and we look at it. We've already seen what is the gain here. V01 by VIC will be equal to GMRC divided by 1 plus 2. 2RE is here. GM times 2RE. So that's the gain of this. Note that this is also a common emitter amplifier. Also a common emitter amplifier, except that there's a resistance here which is not bypassed. But it's a common emitter amplifier. So differential pair, if you look at it, it's nothing but it reduces to a common emitter amplifier here. So ACM voltage gain is GMRC 1 plus 2 GMRE. Okay. Note that common mode gain will be small. Why? Because we have this term here, GM times REE. RE is a large quantity. GM times RE will be large. And so common mode gain becomes small. Differential mode gain, if you recall, was GM RC multiplied by 0.5. So differential gain was large. Common mode gain is small. Okay. What is the resistance looking from here? Common mode resistance here. So we know that it will be R pi plus 1 plus beta times 2RE here. So we can write that as also. So that's the common mode resistance here. Okay. If you want to know now, so this is V01. Note that V02 would be identical. V01 is here and V02, both halves are identical. So if you define a differential output would be V01 minus V02. So differential output will be 0. Ideal case, when the transistors are exactly matched, everything is the same, then the differential output voltage will be 0. Okay. But of course, we know that we cannot make the two halves exactly the same. RC here and RC here will not be exactly the same. Each resistor has a tolerance, and so maybe this may be 1% different from here, depending on how much tolerance is. The resistors will be a little different. The transistors would be a little different. So the differential output voltage will not be exactly zero. In a real life practical case, V0D would be some finite value depending on the mismatches that are there in the circuit. But ideally, differential output voltage is zero. All right, so let's look at our differential pair then. We have two gains. Differential mode gain is 0.5 GMRC and common mode gain is GMRC divided by 1 plus 2 GMRE. As I said, a unique characteristics of differential amplifiers are that they amplify the difference of the two signals and they're supposed to reject anything which is common between them. So a good differential amplifier is which will give you very high ADM and very low ACM. That's a good differential amplifier, which means another way of measuring how good a differential amplifier is by taking the ratio of the two. How large is the differential gain compared to the common mode gain? So if I take the ratio of the two, I get here straightforward 0.5 plus GMRE. So what do we want from a differential amplifier? We want ADM to be very high and we want ACM to be low. But another way of stating the same thing is we want ADM to be high and we want CMRR, common mode rejection ratio, also to be high. Okay, so these are two properties that we are looking for: high differential mode gain, high CMRR. All right, so we have seen earlier that differential mode is like a standard common emitter amplifier, GM times RC. How do we increase the differential mode gain? We know you have to increase the collector current or you have to increase the collector resistance. All of those things we have seen earlier. How do you increase the gain of a common emitter amplifier? Those are the same things here. Let's focus on how do I increase CMRR. Okay. Now, if I look at the expression for CMRR, it may appear to you that, well, CMRR is 0.5 constant. So it may appear to you that what I can do is perhaps make RE large. If I make RE large, I will get a high CMRR. But do you see a problem? If you make RE large, what would happen? What about the bias current? Bias current will go down. Right? Bias current will go down because remember what is the bias current? Minus 0.7 minus VE divided by RE. So if you make RE large, then the bias current will go down. And if the bias current goes down, then GM also goes down. See, it's not as straightforward. So what we can do is we can write down the expressions here. Okay. So GM note is ICQ by VT and ICQ collector current in either of the two transistors is IEE divided by 2VT. See, the current in this branch is, we are calling it IEE. It's not the emitter current, but it's the sum of the two emitter currents here. So IEE by 2VT. And so what we can do is CMRR is 0.5 IEE RE by 2VT. We take the value of GM that you see here, IE by 2VT, and we put it here. Then IEE times RE, we can write it as minus 0.7 minus VE by 2VT. Note that the drop here in this branch, this is minus 0.7 here, and this is VE here, so we can write it here. So it actually does not depend on the value of RE. CMRR, if we write down the values here, CMRR only depends on how large is the supply voltage. As I said, most of the time supply voltage VCC and VE are the same in magnitude, opposite in sign here. So as an example, if I use a fairly large supply voltage, 12 volt, I get CMRR of 217.8. Well, this is not a large quantity. The CMRR that people are looking for from various applications are 10,000, 80 dBs, or 10 to the power 5, 60 dBs is 10 to the power 3, 80 dBs 10 power 4. So we are looking for very large CMRR. But then note that if I look at this expression here, this is only 200. So if I want to increase CMRR, what do I have to do? Well, you'll have to, if you look at the expression, there's nothing else in the expression except VE. I mean, if you don't touch, let's say we're talking about room temperature, so that's all you can do here. So a very high CMRR, if you require a CMRR of 1,000 or 10,000, well, you can calculate, you'll require a very high value of VE. Now, if you recall, we were in a similar situation with common emitter amplifier. In the sense, if you recall that we were thinking, if I want very high gain, If you remember very high gain, GMRC, we required very large value of drop here ICRC and very large VCC. So very high gain requires very high VCC also. And what was the solution for that? We said we don't want to use very high VCC, but we still want a high gain. And the solution for that was we said replace RC by a transistor. Replace it by a transistor which acts like a current source. Alright. So let's see, we are in the same, actually in the same problem, that what we want is a very large CMRR, but we don't want to use a very high supply voltage here. Alright. Okay, just a quick example. Suppose we take 6K here, 5.65. So let's work it through. IE 2 milliamperes, 1.8 milliampere here. GM, ADM is, let's point out 115. RID is 5.2K. Straightforward calculations. ACM is minus 0.53. RIC is 1.14 megaohm. Just note the values. Differential mode gain is high. Common mode gain is less than 1. It's an attenuator. RID is modest because it's only 2 times R pi. RIC is very high, common mode gain, because common mode resistance is very high here. Alright, so back to the same slide here where we said that CMRR is a modest value. 200 is not a very high value because we are looking for something larger. And one of the ways of getting something larger is if I replace this REE by a current source. Note that what is the purpose of RE? The purpose of RE, if you look at what it was this was minus 0.7 and this was VE, and it was the voltage drop from here to here was causing a current to flow, and this current then was biasing Q1 and Q2. So the purpose of RE was to bias the transistors Q1 and Q2 at some value of current. At some value of current. So if I want 1 milliampere here, all I want is 2 milliamperes to flow here. And if you want 2 milliamperes to flow here, then you appropriately choose RE. So another way of biasing that I can think of is, suppose I take RE out. And instead of that, suppose you want to bias it at 1 milliampere here, I put a 2 milliampere current source. If I put a 2 milliampere current source, right, what would happen? If it's a very good current source, I take here and put 2 milliampere current source. Fine, biasing is okay, no problem. Under small signal, what would you do to the current source? If it's a ideal current source, what will you do to the current source? Open circuit. Open circuit means RE is small signal value of the resistance between here and here is infinite. So what would happen to CMRR? CMRR, if you note here, the small signal value here of this particular whatever element you put will go to infinity. But we can't make a ideal current source, so the value of this particular point would have some value here. But what we see here is that we can obtain very high CMRR if I take this resistor out and replace it by a current source. Okay, so that's the strategy for getting high CMRR. This is what we have done. Let's look at this particular schematic here. It's the same differential pair. As I said, we need to bias it at a certain current. So what I've done is, this you would recognize is a current mirror. And look at this current mirror here, VCC here and VE here. Together, what this current mirror will do is, if I start from here and write down the Kirchhoff's law. So I start from VCC, minus the drop here, we come here and VBE and back to VE. So what you can see here is that by choosing an appropriate value of R bias, you'll get a certain current in Q4. You can adjust the value of current in Q4. And Q4 and Q3 are identical. So you get the same value of the current here. First order approximation, you get the same value of current here. So if you want 2 milliamperes current here, well, adjust the value of R bias, so you get 2 milliamperes here. And thereby you get 2 milliamperes of current here. Okay, so biasing is fine, no problem. If I put here 0 and 0 here, this Q4 decides how much current flows in. So we can do the biasing in a straightforward manner here. As you can see, VCC minus 0.7 minus VE by R bias is the current that flows in this branch, which is the same current here. All right. So what about small signal analysis? Under small signal condition, When I look down into my Q3, what do I see? Under small signal. When you look down, what does Q3 appear to you? R0? Because you're looking into the collector of Q0. Note that when you build small signal, what would this point be? Ground. This would be small signal ground. What would this be? Small signal ground here. So everything would be small signal ground. This would also be small signal ground. And what you'll end up getting is that when you look at Q3, you'll see a resistance which is R03, which is equal to early voltage divided by IEE, the net current flowing here. So under small signal analysis, this whole thing appears as a resistor which is very large. And therefore, all results same with this value of RE. ADM is not affected. In ADM, there's nothing about this particular part. ACM will become GM by 1 plus 2 GM RE times RC here. So this will become as usual. So let's write it down here. So you can see here GM times REE. So what do I do with RE? Replace it by R0. Replace it by R0. And how much CMRR do we get? So if you take VA by IE and put it here, VA by IEE, and you have a value of GM, which is this one here. So what do you get? You get CMRR approximately equal to VA by 2 VT. Early voltage divided by 2 VT. If you recall earlier, we were getting CMRR 0.5 plus the negative supply voltage. Roughly the negative supply voltage divided by VT. Now we are getting 0.5 plus the early voltage divided by VT here. And early voltage is large. It's about 100 volts or so. So you get a very high value of CMRR. If you're not happy with that value of CMRR, you want even higher. What do? Look at this expression for CMRR, 0.5 plus GMRE. You want even higher values of CMRR. You want even higher values of CMRR. So the strategy again in CMRR is that if you want, you look at RE. How do you increase RE? RE is when you look into the collector and you see only R0. Now you want even higher value of R0. Higher values of the resistance when you look into the collector here. What can you do? How do you increase when you look down, you want to see a very large resistor. How do you increase that value? As an example, suppose I say I put a resistor in here. I put a resistor in the emitter of Q3. One resistor R here and another resistor R here. When you look down, what do you see then? You see R0 multiplied by 1 plus GM RE parallel R. RE parallel R pi. So you will get even higher. So if you want, put a resistor here. Now in all of this, when we are talking about, if you're noticing, what we are doing is that when you are implementing a transistor on a IC, I made the statement earlier, the cheapest and the easiest to fabricate components are the transistors. Resistors are difficult to make. They occupy more area. And capacitors are impossible to make unless they are very small value. So the general trend in making IC amplifiers is what? Use as much as possible transistors. Don't use resistors and avoid capacitors. Okay? So that's why if you note here, when we went back, we had a resistor here. It does two things. When I replace the resistor by this one here, you may say, well, you've used one more resistor here, so you've not replaced the resistor. But remember what I said was, we can have one resistor, and with that one resistor, I can bias not just my differential pair, but I can bias many other parts of the circuit. I can use another transistor Q4 somewhere and bias another piece of circuit here. So it's only one resistor that I can use and bias many parts of my circuit. Alright? So what we have done is we've replaced the resistor here by a transistor. Transistor is smaller in size and easier to fabricate. And not only that, it's giving us the benefit of higher output resistance, higher resistance also, so increasing CMRR. So the question that I'm asking is, how do I further increase it? Well, we said we can put a resistor here. We can put a resistor here and we can put a resistor here. Then the next question that you can say is, the resistor that I put here, Can I replace it by a transistor? Always see in all your circuits, every resistor that you see here, can I replace it by a transistor? And if you can do that, then that's a better design. As I said, try to avoid resistors as much as possible here. So what we have done is, as I said, we have removed this and use a transistor here. The next thing that if you recall, we said gain of this amplifier is GMRC. Gain is GMRC. And we said, if you want very high gain, then we can take this resistor out and replace it by a transistor. All right, so that's what we'll do. So this is where we are. I'm not showing the whole circuit here. I'm saying we've already replaced it by a current source. Next thing what I'm going to do is take my RC out and put it a PNP transistor here. Note that if you recall our earlier discussion, we wanted to take RC out and replace it by a transistor. We had seen that NPN transistor we cannot put. NPN was not working out. PNP is what? Because when you connect a PNP, then when you look up, you're looking into the collector and you see a high value of resistance. Okay? You see a high value of resistance, and that allows us to build a lot of gain here. So what we arrive at is now we replace this part by a current source. And what we are saying is perhaps we can take this out also, RC, and replace it by 2 PNP transistors here. The advantage that we'll get is, first of all, as I said, RCs are difficult to make, and therefore transistors are much easier. So the whole circuit becomes easier to fabricate, occupies less area. The other one is the transistor offers me a very high value of output resistance, and therefore I'll get very high gain. But note that I've introduced one complication. And the complication is resistor is only 2-terminal. I only take a resistor and just put it between here. Transistor is 3-terminal here. So 3-terminal, which means I have to bias this point also. I have to bias this particular voltage here. I have to find a voltage to bias this one here. And as I've said, there is a problem in biasing. There's a problem in biasing because note that I'm biasing from here. So let's say this is 2 milliamperes. If this is 2 milliamperes, then 1 milliampere should flow here and 1 milliampere should flow here. But then the same current should flow through Q3 also. And same current should flow through Q4. How do I find the right value of V bias such that 1 milliampere flows through Q3? How do I find that? Note that if, let's say I apply 0.7. What is the net volt of, will 0.7 work? Will not work here, because what you need to do is the emitter base voltage, this is PNP, the emitter base voltage has to be maybe close to 0.7 or so, right? To allow the transistor to conduct here. But then note that the collector current of Q3 is exponentially dependent on the base emitter voltage here. So a little bit of error here will cause, instead of 1 milliampere here, may cause 2 milliamperes to flow here. So this, if you don't put the value of V bias properly, this will try to conduct 2, and this one is trying to make it conduct 1, and you get into a problem. This is trying to conduct 1, and this is trying to conduct 2. It's not possible to have, they are in series. So one of the transistor wins, and the one which has a smaller current will win. If this is trying to force 1 milliampere here, and you're trying to force 2 milliampere here, then this transistor will win. You will have 1 milliampere here, and this transistor we can show will go into saturation. Will go into saturation. And the whole amplifier will not work. On the other hand, if this is trying to force 1, and this is trying to conduct 2, then this may win, and then these transistors will go into saturation. So biasing becomes an issue, because we have to, the biasing of this transistor is very, very sensitive to the voltage that you apply. All right. In order to solve that particular problem, let's look at this solution here. What we do is the following. We take, so I just pointed out that V bias is very sensitive. So what we've done is, we've taken V bias here, this point here, and we connected it here. So can you see that this one, this circuit is also like a different, like a current mirror? Current mirror was what? Just go back and see a current mirror circuit. When you see this kind of a picture here, two transistors, one transistor's base and collector are shorted together and the two transistors are matched. This is what we call as a current mirror. Go back and see what we have obtained. Two transistors identical, and of one transistor, base and collector are shorted together. So this is what we are saying is biasing is an issue, and as a solution to that biasing, we are saying if you take this point and just connect it here, just one simple connection here will solve lots of problems. Note that I no longer have to apply a bias voltage. There's no bias voltage which is required now. But you may also be seeing, do you see a problem? First of all, note that the circuit is no longer symmetric. Earlier, the circuit was always symmetric. Q1, Q2, Q3, Q4. It's no longer symmetric. Symmetric would have meant that if I short base and collector here, I should have shorted base and collector here also. Maybe I can do that. I can take here and short this also. But do you see a problem? When I take a transistor and I short base and collector, and you look up now, you look up, what do you see? When you look into the collector of a transistor with its base and collector shorted together, what do you see? This is PNP, so you may be having a little bit difficulty. Try to imagine an NPN transistor with its base and collector shorted together, and you're looking into the collector. What do you see? 1 over GM. That's all you see, 1 over GM. When base and collector are shorted together and you look from the collector side, you see 1 over GM. So when you base and collector are shorted together and you look up, what do you see? This whole Q3 acts as 1 over GM3. And what is 1 over GM3? Very small value. And so how much gain will I get here? Negligible. No gain here. So if you're thinking that I can short it here and I can short it here also, then at both the places I will get no gain. Or gain which is practically equal to -1 or so. But that's why you note that what we have done is we've shorted it together, but we have not shorted on this side. So on this side, when you look up, you're looking into the collector, but collector and base are shorted together. So you see a small resistance 1 over GM. But on this side, collector and base are not shorted together. So when you look up, you see R04. You see a large resistance. So on this side, I'll build up gain. But on this side, I will not be able to build up gain. On this side, I will not be able to build up any gain here, but on this side, I'll build up gain. So what we are doing is we have sacrificed the symmetry. We have sacrificed the symmetry in order to enable proper bias. Now you can see why biasing is proper here. Say this is 2 milliamperes. Okay? If this is 2 milliamperes, you'll 1 milliampere here and 1 milliampere here. Let's say it divides. This 1 milliampere will flow through Q3. Will flow through Q3. Fine. What will it do as it flows through Q3? This is a current mirror. So exactly 1 milliampere flows here. And this also requires 1 milliampere here. So there is no problem. 1 milliampere. See, the whole problem with this V bias was what? That I had to adjust the value of V bias. I had to adjust the value of V bias so that 1 milliampere flows here and 1 milliampere flows here. And that was difficult. How do I find that exact value of V bias here? Now I don't have to do that. If this is 2 milliamperes, 1 milliampere flows here, 1 milliampere will flow here. As this 1 milliampere is flowing through this, it will set up a value of voltage here. 0.7, 0.68, 0.69, whatever it is, it will develop a voltage at this particular point here. Okay? And the same voltage is applied to Q4, so 1 milliampere flows here also. And so therefore, the biasing problem has been avoided. I don't need to apply a external bias voltage here. The bias voltage that you see for Q4 is internally being generated here. Is being internally generated through this current here as it flows. It generates a bias voltage here. So biasing problem has been avoided, and I'll be able to get high gain here. The only problem is I don't get symmetrical characteristics anymore. I will not get gain here. I'll get a gain at this particular point. All right. So the advantages of this one we'll see here. Bias point will be stable, unlike this circuit here. This circuit, as I said, very sensitive to V bias. So this circuit, bias point is stable. I'll get high differential gain, not at here, but at this particular point. High differential gain because I'll get very high resistance when I look up Q4. High differential gain. And we'll also see that we'll get very low common mode gain. It's not obvious looking at this particular circuit that this particular circuit also gives you an advantage in terms of common mode gain. One, of course, is because of the current source, but other reasons are also that it gives you high common mode gain. Again, note, to make it properly work, Q1 and Q2 are matched, and Q3 and Q4 are also matched here. So what we need to do next is take this particular circuit and analyze it in more detail. Analyze the bias point, analyze the differential mode gain, and analyze the common mode gain here. This is in IC amplifiers. I would say, if you have huge number of circuits, and if you do a ranking of circuits in terms of their importance, this circuit would rank at the top, the topmost circuit in terms of importance. It's a circuit in almost all IC amplifiers. You'll find a circuit like this. All lines, whether it's a comparator, multiplier, no matter what you think of, you'll find a block like that. A differential pair with a current mirror load. This is an extremely powerful, very versatile, very useful particular circuit here. And it's very interesting in analog circuits that if you compare this with this, right? This with this, and when we compare them side by side in the next lecture, you'll see the advantages of this circuit with respect to this particular circuit. The gain you will find is doubled. The bias point is more stable. The common mode gain has improved. All kinds of characteristics of this particular amplifier are improved as compared to this. And what is very interesting is, what is the difference between these two? One wire. One wire, that's it. One small connection between here and here will result in, compared to this, doubling of gain. Doubling of differential mode gain. Improvement in CMRR. Bias point stability. One single wire. Okay, one simple connection is all that you do, and you get all these improvements here. All right, so that's what we'll see in the next lecture.